Hello everyone, welcome back to our channel. Today we'll unravel the fundamentals of pulse width modulation and its pivotal role in modern electronic technology by delving into its definition, principles, characteristic, and diverse applications. What is PWM? Pulse width modulation, or PWM, is a modulation technique that varies the width of the pulse in a periodic waveform while keeping a constant frequency. It involves repeatedly turning a signal on and off, with the width of each pulse representing the signal's amplitude. By adjusting the pulse width, PWM allows for precise control of the average power delivered to a load. How is a PWM signal generated? PWM signals are generated using electronic circuits or microcontrollers. The first step in generating a PWM signal involves selecting a reference value, often represented as a voltage level or a digital value. In many PWM generation circuits, a comparator is used to compare the reference value with a varying voltage signal. The comparator generates a digital output based on whether the voltage signal is above or below the reference value. Based on the comparison result from the comparator, the output signal switches between high, on, and low off states. When the voltage signal is higher than the reference value, the output goes high. When it is lower, the output goes low. By adjusting the duration of the high state compared to the low state within each period, the duty cycle of the PWM signal is altered. A higher duty cycle corresponds to a longer high state, while a lower duty cycle results in a shorter high state. Overall, the generation of a PWM signal involves creating a digital signal with a variable duty cycle, achieved through the rapid switching of the signal between high and low states based on a reference value. This method provides an efficient way to control power delivery and achieve desired outcomes in electronic systems and devices. Important parameters of PWM. Several key parameters define a PWM signal, each playing a crucial role in determining the characteristics and behavior of the signal. Here are some important parameters of a PWM signal. The duty cycle of a PWM signal represents the ratio of time the signal is high to the total period of the signal. It is expressed as a percentage and determines the average power delivered to the load. A higher duty cycle results in more power being delivered, while a lower duty cycle reduces the average power. The frequency of a PWM signal refers to the rate at which the signal repeats within a given time period. It is measured in hertz and determines how often the signal switches between on and off states. The frequency affects the speed of response and resolution of the PWM signal. Higher frequencies allow for faster control and more precise adjustments. The period of a PWM signal is the duration of one complete cycle, including the on and off states. It is the inverse of the frequency and is calculated as follows. The period sets the overall time interval within which the signal repeats, influencing the speed and responsiveness of the control system. The output voltage of a pulse width modulation signal refers to the effective voltage level that the signal provides to a load over time. The average voltage delivered by the PWM signal is calculated based on its duty cycle. For example, with a 100% duty cycle and an operational voltage of 5 volts, the output voltage remains at 5 volts. Conversely, with a 50% duty cycle, the output voltage is halved to 2.5 volts. PWM signals find applications in various fields, including motor speed control, power regulation, and signal generation. The ability to control the duty cycle of the PWM signal allows for precise control over the average power delivered to devices. Here we want to highlight two most typical applications of PWM technology in electronics: motor control and signal generators. In motor control applications, PWM is employed to regulate the speed of DC motors efficiently. By adjusting the duty cycle of the PWM signal, precise control over the motor's speed and torque can be achieved, making PWM a cornerstone in modern motor control systems. In signal generators, PWM is utilized to generate digital signals with varying pulse widths, frequencies, and duty cycles. Signal generators equipped with PWM functionality can produce complex waveforms with high accuracy and resolution, enabling engineers and technicians to simulate a wide range of signals for testing and development purposes. In summary, PWM is an incredibly useful and adaptable modulation technique. Its ability to adjust duty cycles and frequencies, combined with its precise control over power delivery, makes it an indispensable part of many applications, from audio amplification, lighting systems, motor control, to power regulation. Understanding the essentials of PWM is crucial for engineers to effectively implement this technology when designing powerful and efficient systems.
Ready to explore innovative PWM-based products and technologies? Head over to ato.com or click the links in the video description to discover a diverse range of PWM-enabled devices and solutions tailored to elevate your projects. Take the next step in testing and development excellence today. Thank you guys so much for being here. We hope this video has provided valuable insights into PWM and its applications. While you're at it, please go ahead and hit that like button for us and subscribe to our channel if you want to learn more about electrical concepts and engineering practices. Don't forget to check out our website, and we'll see you until next time.